Hey folks, Mr. Vote here, coming to you from Hong Kong. By now you know that I'm not in class, obviously. So I came to Hong Kong for the weekend for a science conference. Some of you already know that. And yeah, so a super typhoon came through and it is raging outside right now. So what I'm going to do in this short lesson is just give you some background info and kind of connect some of the things that we did on Sunday, where we were in the back of the room and we were looking at those light up beads. We were talking about the Bohr model. We were looking at those gas tubes and talking about discrete quantized energy, these ideas that electrons can move between energy levels. So we're going to kind of connect that and bring in this concept of quantum numbers and electron configurations. So it's going to be a little bit of me talking and a little bit of me just jotting down some of the key things. So just in general, what you should be doing today, you should have started out with a follow-up problem to how we finished class on Thursday. And that document you would have found on the study guide under the group starter problem. And hopefully the substitute is going to give you or has given you the answer for that as well. If you hear things in the background, like loud noises, those are just crazy wind coming through it's kind of crazy here. So it's just like the doors and the windows rattling. So anyway, back to it. So you should have checked the number 2 on the group starter problem. We did number 1 in class together right at the end of the day, and you should have checked out number 2 and then checked your work. The next thing the agenda said was you were going to review worksheet 01D in small groups. So that was your homework. So you should have completed that and you should have checked it out. To make sure you didn't have any questions. Now, of course, on Wednesday when we all are back together, we'll go over any lingering questions, but you really remember that this class is not done in isolation, so you really need to work together. So this is the video lesson, and where we left off, we were talking about the Bohr model, and the Bohr model was great to an extent. And we looked and we talked about hydrogen specifically. And hydrogen, the simplest atom or the simplest element, has 1 proton and 1 electron. And so Bohr had these predictions. And what we saw for visual evidence in those atomic emission spectra matched the mathematics that he calculated for these transitions between energy states. So everything was looking good, but when we applied this model to more complex elements, so elements that had multiple protons and multiple electrons, or polyelectronic atoms, we found that it didn't quite work so well. And so we kind of took this model and it had to be modified over a number of years in various ways. So, I guess the first major point is that the Bohr model, it was a good working model. And I'm just going to kind of do it like this. So this is going to be like a mini lesson. So the Bohr model was great, up to an extent or up to a point. So the Bohr model worked, but it really only worked with hydrogen. The calculations didn't follow through for the other elements. But what it did do is it did show that electrons do exist in very discrete locations, and they gain energy and they release energy in very discrete amounts, and that's indisputable. But some of the details are and needed to be adjusted. So Bohr model dealt with hydrogen, and we have quantized energy. That's for sure, but what it isn't is electrons do not move in specific orbits like what the Bohr model predicted. So electrons in paths or orbits, that wasn't so much correct. So I'm just going to cross that out. Okay, so yeah, that needed to be adjusted. So in terms of scientists, there were a couple of different scientists that really kind of had some breakthroughs. One particular scientist, his name was Heisenberg. Another one was Schrödinger, and you may or you may not be familiar with those names, but what they really did was they applied a mathematical basis to this, and they developed what's often known as the quantum model or the quantum mechanical model. And if you were to look in the side of the classroom, what you would see on those posters that we talked about the other day, we kind of stopped at the Bohr model, but the quantum mechanical model really kind of picked up where it left off, and it gave some very specifics. It said that, that these orbits that we were talking about, they really took this idea of orbits and replaced it with a concept of an orbital. And what an orbital is, in mathematic terms, is it's a wave function. And, well, what the heck does that mean? Well, in short, it's a mathematical algorithm, or it's a mathematical formula that predicts where an electron will be in a certain proportion of time. So in this case, an orbital or a wave function says that it's the likelihood or it's the location of an electron where it will be like 90% of the time. So yeah, that's kind of the idea. So maybe what we can say is it's just it's a region of space. Yeah, it's a region of space, and the electron is there most of the time, but we don't know for sure. That's the last thing that we can put. Like, we don't know for sure. So we can kind of go with that, and then kind of get into some of the nuts and bolts of of the actual lesson. So one of the things that the Bohr model had talked about was these discrete energy states, and for a hydrogen atom, I'm going to slide this over a little bit. For hydrogen, what he had reasoned was that electrons can exist in these orbits, and he called these orbits like a 1s and a 2s, and what we really have here is an axis with increasing energy. So electrons would move from one orbital to a discrete second orbital. I'm going to write it proper like that. And so they could only go to certain places by absorbing energy, and then they'd release energy, returning back down to ground state. And so one thing that this model of a single atom, hydrogen, really kind of described was this term called degeneracy, or degenerate orbitals, where these orbital types all exist sort of with the same energy. But if you think about what we've learned in regular chemistry, is that electrons fill in certain locations, like they fill in a certain order, and this model just didn't support some of the later evidence, so it had to be adjusted. So if we think about an orbital is essentially the probability of an electron being in a location. So if we think about it on a graph or graphically, we might think of it as like, if this is the distance from the nucleus, and this is going to be the probability, if we're looking at a given electron, there's going to be some probability distribution. So for example, maybe if it's the 1s, it's more than likely going to be in some general location. And so maybe its probability distribution looks something like this, where it says most of the time it's going to be here, but some of the time it's going to exist either further away from the nucleus or closer to the nucleus. But in general, it's going to exist in a certain place. So that's sort of this idea of probability. Now, interestingly, what we found is that when we define these orbitals, like with the letters S, P, D, and F, what we found is that these actually, there's a pattern to how the electrons fill, and the pattern was something like this, where N is a variable, E is energy, and S is lower in energy than the P's, which are lower in energy than the Ds, which are lower in energy than the Fs. So what that means is that electrons would fill the S first, then the P, then the D, then the F, and we have this predictable pattern that we now know. But back in the day, if we're thinking about this single electron atom, well, why would it fill the S before the P's if they're all degenerate, or if they're all in the same energy range? And that's really where the wave functions help kind of bring some clarity to this. So what we have to think about is looking at the probability distribution. So we're going to use the same axes here. The probability distribution for electrons in a given, what we call a given subshell. So S, P, Ds, or Fs. So if we were to investigate, let's say the 3s, for example, what we might find is the probability distribution might look something like this, where maybe it kind of looks like that. So we can label this the 3s. So what this is really saying is that, okay, so the electrons in the third energy state that we call S, most of the time they exist out here, but some of the time they're found here, closer to the nucleus, and some of the time they're found even closer, but most of the time they're here. So if we compare the P's now, what we might find is the P's, I'm going to go to a dotted line here. Okay, so the P's might, its probability distribution might look, I don't know, something like this. Now what we notice is predominantly the P's are actually closer than the S's, but we have these regions of space here for the S's that actually add up to more time or a higher probability of this, the 3s being closer. So this little bit right here, this is something referred to as the penetration effect. And why is it really important? Well, it's really important because that defines the energy of each of these S, P, Ds, and Fs. So that was something that was strikingly different from the single hydrogen atom model to the polyelectronic model, basically every other atom except for hydrogen. So what that then told us, and if we compare the Ds, I'm going to go dashed. So the Ds might look something like this. And so, the Ds, they look like probability-wise, they're almost actually closer than the S's. But again, this penetration from, a larger proportion of the P's and the proportion of the S's, basically what that means is if there's a larger proportion of time spent closer to the nucleus, then it's going to have a lower amount of energy. And so when we think about the way that electrons go into an electron configuration, S's would be lower in energy than P's, lower in energy than D's, etc. And that's what's really going to build the electron configuration idea. So now going from there, we've talked a little bit about, right up at the top, let me just slide this up. Okay, so we've talked a little bit about the Bohr model and the limitations of it and how it worked really well for hydrogen, but there were some issues. So one of the issues was that hydrogen was a single electron. And so we could measure that, and we had some good evidence to realize that electrons made quantum jumps, and we can mathematically determine those jumps, but it didn't work so well with others. So this new probability model allowed us to identify where electrons were according to these complex mathematical equations based on probability. So from there, what we can kind of do is we can turn our attention to these things that we call quantum numbers. And a quantum number is essentially just the characteristics of any given electron. So let's take, for example, hydrogen, the most simple atom in terms of electronic structure. So for hydrogen, its quantum numbers would contain 4 parts. There would be a 1, an S, a 1, and then there would be an arrow. And we're going to define what each of these represent as well. So the 1 tells us the energy level. So think of that as sometimes referred to as the shell. So hydrogen, its energy level is 1, so it's in the first shell. The S tells us what the subshell is. So S, P's, D's, and F's we refer to as subshells. The 1 tells us how many electrons are actually present in that given subshell. So number of electrons, and then this tells us the spin of the electron. And basically what we found magnetically is that electrons either spin up or spin down, but it's not really that easy. But we just give an up or a down arrow just to kind of make some sense of it. So these are our quantum numbers, and think of it sort of like an address for an electron, okay? Keep that idea in mind. So if we were to move to the next element is helium, and it's a 1s2, and its electron is going to be downward. And we'll kind of get into how we actually determine these as we define each of the rules. So these are just some simple electron configurations. Okay, cool. So, and really what these are, I guess technically these are what we call our quantum numbers. So the configuration would be all of the electrons if we were to look at an atom that's a little bit more complex. So essentially the rules for electron configuration filling, there's 3 basic rules. And first rule is that electrons fill from lowest energy up. And so that comes back to this whole model where, electrons will fill the S's first, and then they'll fill the P's, then they'll fill the D's, then they'll fill the F's. So that's the first general rule. That's called, you don't really need to know this, but this is called the Aufbau rule. Okay, the second rule, electrons, when they go into these orbitals can fit a maximum of 2 electrons. So 2 electrons max, and they have to have opposite spin when they go in, opposite spin. So if we look at hydrogen and helium, the 2 electrons that make up helium, the first one has a spin upward and the second one has a spin downward. So that's what this represents, and this is called the Pauli exclusion principle. Pauli exclusion. And the third says that effectively, depending on how many orbitals we have in a given subshell, okay, so how many orbitals within the S or the P or the D or the F, that electrons are going to fill the orbitals equally first before they double up. So it's like the equal energy rule. And this is called Hund's rule. Yeah, Hund's rule. So we got Aufbau rule, Pauli exclusion principle, and Hund's rule. Okay, so let's take a look at how something like this would play. And what I'm going to do is I'm just going to open up, give me a second, I'm going to open up p-table. Just our online source. So here we go. And what we're going to look at is, carbon. Why not? Okay, so carbon. So carbon is going to be element number. Sorry, hang on. I'm having trouble with my Wi-Fi, of course. Okay, so it's going to be element number 6. So it's going to have 6 protons, 6 neutrons, and 6 electrons. So when we write an electron configuration, what we would do is we'd start with the element, and then we would fill from lowest energy to highest energy. So in this case, carbon, it's going to begin, we're going to fill 6 electrons, so 6 electrons, and this is going to fill in as a 1s2, a 2s2, and finally a 2p and 2,4, and this is going to be a 2p2. Yeah, so, okay, now let me get to where I need to go. So I've got a visible reference. Okay, cool. So the way that we could represent this would be what we call our full electron configuration. So that's full. If we want to do what's called a noble gas configuration, noble gas, that's going to be, so what we're going to do is we're going to take the nearest full configuration of this, and we're going to say, oh, that's helium's configuration. So for carbon, it's got helium, so we're going to put that in a bracket. That's noble gas configuration. And then we just fill up the rest. Now, with this, it doesn't look like we're really saving any work, but when we go to this shorthand noble gas configuration, for bigger elements, it's going to save us some time. So if we wanted to draw what are called box diagrams, what those are going to do, those are going to actually allow us to see the orientation of the electrons. So a box diagram might look like this. So we know we've got a 1s, and we know we have a 2s, and we know we have a 2p, and in the p's, we're going to have 3 specific orbitals. So this is the 2p, and this is x, y, and z. So we have 2px, 2py, 2pz. So if we're filling 6 electrons, following off-ball principle, the first electron goes here, the second one goes here, and now what we're doing is we're fulfilling all of these principles. We've filled from the lowest to the highest, 2 electrons per orbital, and this is an orbital, this is an orbital, these are 3 orbitals. Okay, and then the following one says the equal energy rule, or Hund's rule. So before this electron fills downward, this just has to be, all orbitals have to be equally full. But since S only has 1 orbital, then, well, we just fill up and then we fill down, and then that's good. Okay, we come up and we fill in 2s2 up, 2s2 down. And then now we get to this one, and now we're going to see where Hund's rule comes into place. And Hund's rule says we're going to fill across first. So we're going to fill an x first, and then we're going to fill a y. We're not going to fill x downward. So could this electron fill in the z instead of the y? And the answer is absolutely. Now, we just write this because it makes sense for us. So if we were to go to the element beyond carbon to, let's say, nitrogen, nitrogen is a 2p3. So it would have the identical box diagram, except now we would have 1 more electron all facing parallel. If we went to a 2p4, this is nitrogen. Now what Hund's rule says is now the electrons will fill with anti-spin or anti-parallel spin, opposite spin, Pauli exclusion. Could it have filled the Y? Well, yeah, of course. Could it have filled the Z? Absolutely. So what we're seeing is that we have a number of different patterns starting to form. All right, now a couple bits of terminology here. So what we notice is that when we have electrons that are filled here, we're going to see that effectively their spins, will effectively cancel out. So what we can call this, because there's 2 spins canceling out, this is diamagnetic. Okay, so these are diamagnetic electrons. Now, if we look at the overall entire atom, we can determine if the overall element is diamagnetic or if it's something we call paramagnetic. So if we look, we say, are all of the electrons paired up? And we say these are, but these 2 are all alone. So these are referred to as paramagnetic electrons. And if we have paramagnetic electrons, then we have a paramagnetic element. Okay, so now why is that important? Well, if we think about magnetism, for example, when we have electrons that are all by themselves, they can be influenced by magnetic fields. So we can sometimes describe atoms or ions as para or diamagnetic. One of the things I'm going to ask you to do is to watch a short video. And the video is, it's a video I made last year and when I was teaching in Dubai. And I want you to watch it, and it's going to be a digital lab that you're going to put in your lab notebook. And what I want you to do is think about the electron configurations of the elements that are in the demonstration. and see if you can determine which ones are para and which ones are diamagnetic. Just remember, and if you'd be able to write their configurations themselves, that would be pretty amazing. So we have covered quite a bit in 25 minutes. So what I'm going to refer back to is the study guide. And first, I'm just going to tell you in the Zoom doll text, you're going to find that everything that I just covered is on pages 310 to 329. And you're going to want to kind of dig in a little bit there. If you get stuck anywhere, there's tons of examples. Remember, nothing's as good as having the teacher there to answer all those little questions, but the book does a pretty good job. And we're going to come back to this on Wednesday and have some more discussion and all that good stuff. But the text fills in a lot of that. So what I want you to do for Wednesday, when I'm back and when you guys come in, you should have 01E and 01F done to the best of your ability. That's what the study guide says. And you're probably gonna have to reference the textbook or maybe slow down and go back to this video a couple times, but just do your best, no worries. Then you're going to watch the video, the magnetic ions demonstration. It's a digital lab, and you're going to go ahead and just drop it into your notebook. I think it's lab number 5, just like normal. Do an aim, do a very short procedure, just diagram what you see in the video, and then a little data section and what you think is actually going on. So obviously you're going to be writing or drawing these little diagrams here. Sometimes, they might be called box diagrams. In the worksheets, you're going to see them actually as boxes. So, so you're going to be working on that, and that's pretty much it. Now, just one note, some of the notation that you're going to see is, especially with the p orbital, you're going to see like x1 or y, y2. So these are just referring to the actual orbital orientations. So just one closing note, the reason that there's one orbital for an S an S wave function is that the shape of it is actually spherical. And so the only way that a sphere orients around, the nucleus three-dimensionally is there's one orientation. But the P, I think of P as like a peanut. So the actual shape of the orbital, it has 2 lobes like this. And so you can orient it X, Y, and sorry, my camera doesn't really, but think of like one coming at you. So it's like X, Y, and Z. So therefore there's 3 orbitals. The Ds, there's actually going to be 5 orbitals because it's a more complex shape that can be arranged on the XYZ axis in different ways. Now, just a note, as you're going through the book, you do not need to memorize shapes. You don't need to memorize planes or orientations. And we really limit just shapes and orientations to S's and P's. That's it. So, D's have 5 orbitals, but we don't have to know what they are, nor do we have to know the shapes. So remember, it's not about memorizing. Again, it's about learning it. So I hope that this video has helped, and I realize, it's 30 minutes long, but also we probably would be talking for close to an hour in class. So technically you're getting 30 minutes less of me talking, so you're probably pretty happy about that. All right, so I'm out. I'm gonna get this uploaded, and if you guys have some questions, just, you can see me on Tuesday. I'll be back in the flesh. Otherwise, just hang on to those, get some work done, make some progress, and we will see you Wednesday. All right, take care.